class, tonight I want to cover 5.3, the fundamental theorem of calculus. And this is what the theorem that we're going to use to integrate. So the fundamental theorem of calculus says, suppose that f is continuous on the closed interval from a to b. If g of x is the integral from a to x of f of t dt, then g prime x equals f of x. So the first part of the fundamental theorem of calculus is really about a derivative. The second part says if the integral from a to b of f of x dx equals big F of b minus big F of a, where big F is any antiderivative of little f. So that is the derivative of big F is equal to little f. So they're just saying to integrate, you find the antiderivative of the little f and you evaluate it at b, and then you subtract and you evaluate it at a. So I'm going to try to explain this using the velocity curve that we talked about. We saw that the area under the velocity curve from t equal t1 to t equal to t2, assuming v of t is positive, is the total distance traveled. Now, if the velocity curve is not necessarily positive, so what that means is that some of the curve goes below the t-axis. So this is a picture of a velocity curve. Then this integral would be the displacement or the net change in position. The position function is s of t, so the integral of v of t dt would be the antiderivative of vt, so that would be s of t evaluated at b minus the position function evaluated at a, and this is the displacement. Also note that s prime t equals v of t, i.e. s of t is the antiderivative of v of t. So what we're saying here is that, like with the velocity curve, we know that if we integrate, and so we're looking at v of t times tx, really, if you think about the approximation in the rectangles, then and if you remember back in the previous section, we add in the area above the curve and we subtract the area under the curve. Then what we really need to do, what the second part of the fundamental theorem of calculus is saying, is that if we find the antiderivative, which is the position function, and evaluated it at b and then evaluate it at a and take the difference, that will give us this displacement. So that's what part 2 is saying. Now I'm going to try to explain part 1 using part 2. So this is what part 1 says. So we're saying if this function g of x, and notice it's the integral from a to x of f of t dt, then g prime x equals f of x. So think about the velocity curve, and g of x is this function right here. Now, if you think about what part 2 said, it said find the antiderivative of v of t. Well, that's s of t. So if we evaluate s of t at x and then at a and take the difference, and this is a constant because a is a constant, if we take the derivative of that, then we'll have the derivative of this side, and that means s prime x, and since this value is a constant, its derivative will be 0. So in other words, g prime x equals v of x, because that's s prime is v. So the derivative of the integral from a to x of v of t dt is v of x. Okay, so you have to be kind of careful not getting this confused. When you see a problem that's concerning part 1, a lot of times students will get confused and think it's about integration, but really it is about integration, but really we're trying to find a derivative. So for example, let's look at a problem like that. So here's the fundamental theorem again. Remember that g prime x is equal to, that should be an equal sign, f of x. That's what we're going to use. So we want to find the derivative. When it says find the derivative and it gives you an integral like this, they mean use part 1. And so the derivative of this function would be, you really just take this function and put x where t is. That's really what you do. It doesn't really matter what constant this is down here, but the x needs to be at the top. Okay, now if I did this same problem using part 2, because I could in this example, I could actually integrate this. So this is a different way to do it, and then take the derivative. So if I integrate this, the antiderivative would be 3t plus 3 cubed over 3. And if I evaluate that at x and 0 and then subtract, I get substituting in the x and then substituting in the 0. And so I get 3x plus x cubed over 3. Now, if I take the derivative of that, I get 3 plus 3x squared over 3. So g prime x is 3 plus x squared. That's the same thing that I got right here, 3 plus x squared. So a lot of times in the problems when it asks you to find the derivative, you won't be able to integrate this part. So you really have to use part 1. So part 1 really says that you just, to find the derivative, you just take the integrand and replace the t with x. And that's what we did right there. Okay, some more examples. So I want to find g prime x, and so all I do is go x squared sine x. We don't even know how to integrate this yet. We'll find out in Calc 2, but right now we don't even know how to do that. Here's another example. So using part 1, I just replace the integrand. I replace the t with an x. Here's another one. I just replace, now this one's a little different because I do have the x at the bottom and it needs to be at the top. So if you remember from one of our theorems, if we interchange the endpoints, we change the sign of the integral. So then I just replace the t with the x, and that's my answer. Okay, because we're taking a derivative, sometimes we need to use the chain rule. And, that's when we have a composite function. And that's when, because remember, this is a function of x, not t. So if instead of x at the top of the integral, we have a function of x, that means it's a composite function. And we're going to have to use the chain rule. You can think of it like this if you want to. G of x is a composite function where the outside function is this integral and the inside function is square root of x. So this square root of x right here, or whatever it is, if it's a function of x, it's the inside function. So using the chain rule, when we take the derivative of this function, we're going to take the derivative of the outside, which is the integral, and we're going to replace the t with square root of x. So this is the outside function evaluated at the inside, but then we have to go times the derivative of the inside. So I multiply times the derivative of the square root of x. So really when you have to use a chain rule, and that's when this is a function of x, not just plain old x, then you do it the way you would do it normally, but you have to multiply times the derivative of whatever this is. So here's another one. So you notice we have sine x. So we replace the t with the sine x, and then we multiply times the derivative of sine x, which is cosine x. Okay, so the fundamental theorem of calculus part 1, if f is continuous on the closed interval from a to b, then the function g defined by, and this is the function g, is continuous on the closed interval from a to b and differentiable on the open interval, and g prime x equal f of x. So this function g of x that we're talking about, say that this is the curve y equal f of t, then g of x is the integral of f of t. So it's the area under the curve of f of t, but it's a function of x. So if x is right here, it means there's this much area. But x is the variable, so if x moves over to here, we get more area. So this is really a function of x, and it's the area under the curve depending on x. So x varies between a and b. G of x depends on x, not t. If f is above the x-axis, meaning the function is greater than 0, we think of g of x as the area under the curve of f of t so far. Okay, so we could call this, think of this as the area so far. So let's look at an example using that. So let's let the integral g of x be this integral, where f is the function whose graph is shown. So this graph in pink is f of t. And then we want to evaluate g, and g is the area under the curve so far at different values of x. So now g of 0 would be the integral from 0 to 0, which would just be 0. Now g of 1 would be the integral from 0 to 1 of f of t dt. So really, it's from 0 to 1, it's this area which is made up of a rectangle with base 1 and height 2. So the area of a rectangle is length times width, or base times height, whatever you want to call it, and that'll be 2. Now, g of 2 would be the area from 0 to 2. So what you can do is you can go ahead and add in the area for the from 0 to 1, and then you calculate the area for this part right here, which is made up of 2 squares and a triangle. So you take the 2 from the previous step, and then you take the triangle is 1/2 the base is 1, and the height is 2. And then we add in the area. You can think of it as a rectangle or 2 squares, but it's 1 times 2. So I get 5. Now, g of 3 would be, 3's right here. We need to take what we already have and add in the area of this triangle. So the area of the triangle, the base is 1, and the height is 1, 2, 3, 4. So if we add, I take the 5, I add in the area of this triangle, that gives me 7. Now notice for g of 4, the graph of the function is below the t-axis. So what I'm going to have to do is subtract this area from the area that I already have. So I take the 7 that I already had, and this is 1, 2, 3, 4. So we've got to subtract that. That's a triangle. It's 1/2 the base times the height, which gives me just a 1/2. And then I subtract 1/2 from 7, and I get 6.5. That's what that should be. It looks a little funny. Then g of 5, I'm going to subtract some more. So I'm going to take the 6.5, and I'm going to subtract the area of this square plus this triangle. The area of the square is 1 times 1. The area of the triangle is 1/2 1 times 1. And that gives me a 1.5. So I'm subtracting 1.5 from 6.5. So that gives me 5. And then for 6, I need to subtract the area of this rectangle, which is 3. And then the B part says, on what interval is G increasing? Well, logically, you can see that it's increasing until we start subtracting. So it's increasing from 0 to 3. You can see that. That's the interval. It's increasing from 0 to 3. Another way to think about it, though, is you think about what we learned in Chapter 4. Now, this function, or f of x, is the derivative of g of x. If you take the derivative of the area function, you'll get f of x. Whose graph would be the same way. It doesn't really matter what the variable is here. And so this is the derivative, and the derivative would be 0 right here, and it would be up until that point, the graph is positive. And so if it's positive, that means that the function is in g of x is increasing. So g of x is increasing on the interval from 0 to 3. Now the C part says, where does g have a maximum value? Well, logically, we can see that it's at t equal 3 or x equal 3, because that would be, we keep adding until we get to x equal 3, and then we start subtracting. But another way to think about it, using chapter 4, what we learned in chapter 4, if this is the graph of the derivative of g, then, and we're talking about where does g have a maximum value, not where does this function that's graphed have a maximum value. Well, if we think about where it has a maximum, it's going to be at a critical number, and that's where the derivative is 0, and this is the derivative function, and it's 0, and it's going to be a maximum if the derivative changes from positive to negative at that critical number, which is what happens right here. It changes from positive to negative, and so that's where the maximum value is. Okay, so let's see what else we have. Here's just the fundamental theorem of calculus again, and this is just a page exclaiming the importance of this theorem. So part 1 can be written this way, that if you take the derivative of this integral, you get back f of x, which says that if f is integrated and then the result is differentiated, we arrive back at the original function. Since the derivative of f prime, big F prime x is equal to little f of x, part 2 can be written, and if we integrate and the big derivative of big F of x is equal to f of t, that's because big F of x is the antiderivative of little f of x, then we get f of b minus f of a, big F of b minus big F of a. So that's saying that if we differentiate a function and then we integrate it, we get back at the original function, but evaluated at b and then at a. Okay, so if we first differentiate and then integrate the result, we arrive back at the original function f, but in the form f of b minus f of a. Taken together, the two parts of the fundamental theorem of calculus say that differentiation and integration are inverse processes. Each undoes what the other does. The fundamental theorem of calculus is unquestionably the most important theorem in calculus, and indeed, it ranks as one of the great accomplishments of the human mind. Okay, so this is just our table of antiderivatives that we had before. We don't worry about the hyperbolic cosine and sine. We're just going to do a definite integral here. So I want to evaluate the definite integral. So we'll change the square root of x to the 1/2. And then I'm going to simplify by breaking it down into terms and then simplifying each term. So remember, you take the exponent in the numerator and you subtract the exponent in the denominator, and then we find the antiderivative. So we're using the power rule here for integration. We add 1 to the exponent and we divide by the new exponent, and then we go plus c, but actually you don't have to do plus c when it's a definite integral because it'll get canceled out anyways, so it doesn't really matter. And then I'm going to simplify this a little bit before I substitute in the values. So then I substitute in the 9 and the 1. I substitute in the 9, I substitute in the 1, and then this just means the square root of 9 cubed, which would be 3 cubed, which is 27. And then I collect my terms, and notice that the c's cancel here, and so I get 28 over 3. So when you evaluate a definite integral, this is a definite integral, you get a number. It's a definite integral because it has numbers here. it has values for your endpoints. An indefinite integral wouldn't have anything written right here. And so we get a number. If you have it in this form, you want to go ahead and multiply it out and collect your like terms, and then you'll be ready to integrate. So we use the power rule in reverse. We add 1 to the exponent, we divide by the new exponent, and then I substitute in the 4 and I substitute in the 0, and I simplify and I get negative 28 over 3. Another problem, and I believe this is the problem that I did during class, that I did the hard way with the limit, and so now I'm doing it the easy way with the rule. So I believe this is the one, and I got 21. So I use the power rule. I add 1 to the exponent, divide by the new exponent. I substitute in the 4 and the 1, and I get 21 as my answer. Here's another one. So I've got to find the antiderivative of secant theta tangent theta, but the antiderivative is secant theta because the derivative of secant theta is secant theta tangent theta. So I find the antiderivative, I substitute in the pi over the 4 and the 0, and it's easier for me to think of secant theta as 1 over cosine theta. And so I substitute in pi over 4 and I substitute in 0. The cosine of pi over 4 is square root of 2 over 2, and the cosine of 0 is 1. And then I just take the reciprocal of this, and you don't have to rationalize the denominator. This is the exact answer. And another example, we want to simplify it first. So I'm going to divide each term by x cubed, and then I'm going to rewrite it with, well, this term, I'm going to rewrite with a negative exponent. This one I'm not, because it doesn't matter, but on this term, I'm not going to use the power rule. Now, on this term, I do. I add 1 to the exponent, and I divide by the new exponent, but the antiderivative of 1 over x is the natural log of the absolute value of x. So in this step, I found my antiderivatives, and then I just simplified it a little bit, and then I'm going to substitute in the 3 and the 1. I substitute in the 3, I substitute in the 1. Now, and then I just write it out, distribute the negative. But the natural log of 1 is just 0. What power do I raise e to get 1? That would be the 0 power. And so this is my answer. I collected like terms, so I added these two terms together, and this is the exact answer that I want. Okay, that concludes today's lesson over 5.3, so hopefully you can do your homework. Talk to you later.